Next, we're going to look at the step in hypothesis testing where you choose a significance level. So this is really important to do before you calculate anything, before you calculate your p-value or gather your data. It's really important that you have decided what is your own threshold for changing your mind, right? That's really what this is. And the cutoff should not depend, or does not depend on the data. It needs to be chosen before the data is collected and definitely before you calculate your p-value. The history behind this, so this whole idea, this whole framework of hypothesis testing in this frequentist viewpoint was really pioneered by this statistician Fisher. And some of his guidelines on this whole topic really said, okay, sure, I'm just going to choose 5%. That seems like a reasonable cutoff for me. And if that doesn't seem like high enough odds, you can cut it down even further. You could look at 2% or 1%. And so really, I highlight this because somehow historically, we kind of took these gold standards of 5% and 1% and just ran with them. But really, you should be making this decision based on the context of the data, the impact of, your default action, and really what you will need to change your mind. So you don't have to get stuck in the conventions of 5 or 1%. You just need to choose something that you can justify and decide on it before seeing the results, and then don't change it. So those are some key guidelines. I want us to think a little bit more about how that value will affect some possible errors we may or may not see. So let's go back to this idea of now we have 500 students enrolled in this class. We're going to give each of them a separate coin. We're going to have them toss it 160 times to test whether or not the coin is fair. So our null is that the coin is fair, and the alternative is that the coin is not fair. We'll just do a complete mathematical complement. So for our test statistic, we have lots of options, but here we're just going to use the number of heads. But now think about it. If I just use number of heads, I'll be stuck because I want to be able to test if I'm both high or low. So I could say number of heads minus my expected number, which would have been 80. And then I need the absolute value of that, because that will now allow me to check for both high and low values. My significance level is 5%. I just chose that. So let's say I'm just choosing 5% based on standard conventions. Now, suppose in reality all of the coins actually are fair. Approximately how many students will conclude that their coins are unfair using this hypothesis test? Take a minute and see what you come up with. To get some intuition about this question, let's actually go simulate it. So I'm in the hypothesis test folder using the hypothesis test errors Jupyter notebook. We are going to set up this scenario where we have the 500 students. Each student is going to flip a coin 160 times. They're trying to test this null hypothesis, and we're using 5% as the cutoff. Now, unbeknownst to them, we gave all of them fair coins. And so we want to know how often will they incorrectly reject the null hypothesis. So notice what is going to happen here. In order to reject the null, they're going to need to get a p-value that's less than or equal to 5%. Let's simulate some p-values here. So here's our test statistic, and I can simulate my distribution of the test statistic here. So let me just do it for 10 flips. Again, these numbers you notice are absolute values from 80. So this, for example, was either 12 above or 12 below 80, and 1 above or 1 below 80. Now we're going to plot this distribution. This is our distribution of the test statistic. Now we're going to go and take a fair coin and have a student flip it 160 times and see how many heads they actually get above or below 80. So that's what's happening right here. And so here is, let's do one student. Okay, we had a student do this. They ended up getting 6 heads, either above or below 80. So they either got 86 or 74 heads. And so if we go look at this on our test statistic distribution, that means their p-value is this area to the right here, which is a pretty big number, right? That area ends up being around 38%. So they would definitely fail to reject the null. They would say, we have, our data is consistent with the null, that this was a fair coin. Then you could have yet another student do this. So let me clear this. And that student is going to get a different p-value. So their p-value is 70% because they got an even smaller value here. And so it looks even less likely, right? Their p-value is very large. They definitely are going to fail to reject the null. So at the end of the day, we want to see how many of these students are actually going to get these very unlikely chances here of so many flips that were so far away from 80, right? And so if we do this with not just 1 or 2 or 3, but we do this with 500 students, that's what we have here, we're now going to print how many of them have a p-value less than or equal to 0.05. And if you're thinking, well, let's see, this is the distribution they're all sampling from, so it should be roughly 5%, right? Because I'm trying to ask 5% of the time I'm saying they're going to get some value way out here, so we would think 5% of the students should end up with that value way out here. You are correct. So how many of these 500 students will incorrectly reject the null? It should be about 5%, which is about 25. Now here I just did it once, right? And I got 18. If you keep doing this over and over, you're going to get numbers that are going to bounce around 25, because 25 is the actual correct theoretical number that we got it there. Third time's a charm. But yes, that is the downside to this process, right? Is you can have an actual fair coin, and if your cutoff is 5% for your significance value, then if the null is true, 5% of the time you're going to incorrectly reject the null just by chance. Just happen to have a really strange, unlucky number of heads with this fair coin, and it leads you to think that it's not fair when in fact it really was. Okay, so what we just showed in our demo is we would expect approximately 5% of the 500 simulations to incorrectly reject the null. And we can see this here. If your significance level is 5% and the null hypothesis happens to be true, there's a 5% chance you will make the incorrect conclusion from your hypothesis test. And this is just the reality of this setup, that sometimes we are going to be wrong. There is a chance that we will be wrong when we set up hypothesis tests and make conclusions from them. So a big question you can ask yourself when choosing your significance level is really, what is your tolerance for that error? Are you okay with this 5% of the time? If the null was true, 5% of the time you would be wrong. That's where sometimes people will choose a lower cutoff because they're less comfortable with that margin of error. So I'm adding to the slide that we just had about the significance level to point out that not only is it your threshold, and not only does it not depend on the data, but it's an error probability. And so you get to choose that cutoff as a way of dialing the knob and trying to control that error. I want to contrast this with the p-value because this is often an area of confusion for students. So the significance level is something you pick, doesn't depend on the observed data or the simulation. It's your acceptable probability of rejecting the null hypothesis when it is true. Common conventions are to use 5% or 1%, but I showed you in this video that was really just out of historical convention, and it should really depend on the context of your data and your decision. The p-value, on the other hand, is something you compute after gathering your data. It depends on the data and the simulation, it is a conditional probability, and it is not dependent on your significance level. So now we're going to look at how we can take your significance level along with your p-value to make your conclusion about your test.